Once Voskhod 2 was in orbit, the two cosmonauts, Belyaev and Leonov, placed the inflatable airlock in position. The airlock was then pressurized so that it was safe for the cosmonaut to enter. Equipped with oxygen supplies, cosmonaut Leonov entered the airlock and attached himself to a safety line, sealing the entrance to the capsule behind him. Next, Leonov depressurized the airlock so that he could open the external hatch and leave the craft. After spending 10 minutes floating in space, Leonov returned to the airlock, closing the outer hatch behind him. The airlock was then repressurized. The hatch to the capsule was opened, Leonov returned to his seat, and the airlock was jettisoned. Cosmonaut Titov's orbit in Vostok 2 took him around the world at an angle to the equator. The cross indicates a certain point on Titov's first orbit over Russia. Because the Earth is constantly rotating, each time Titov completed an orbit, the ground beneath had moved further east. Titov continued to orbit the Earth, but as time elapsed and the Earth continued to rotate, Vostok 2 was no longer traveling over the Soviet Union. 17 orbits and 25 hours later, Titov's orbit once again took him over the Soviet Union. He re-entered the atmosphere to land safely, becoming the first person to have stayed in space for a whole day. This set of scales is balancing two packages of matter that are of equal mass. The matter on the right is radioactive and therefore unstable. It is undergoing a gradual conversion into pure energy gamma radiation. As this energy radiates away, the package loses mass. This causes the scales to become unbalanced, and so they rise on the right-hand side. A very massive main sequence star fuses its gases to form the progressively heavier elements helium, carbon, oxygen, and silicon. Each element is formed initially in the core and subsequently in a shell around the core. Eventually, the core is surrounded by shells of successively lighter elements, each undergoing fusion to produce the next heaviest element. Finally, the silicon fuses to form an iron core. When the iron begins to fuse, the star explodes as a supernova and its outer layers are blown off at thousands of kilometers a second. The collision theory argues that an asteroid about the same size as the planet Mars smashed into the Earth over 4 billion years ago. The two objects partially melted in the heat of the impact, and chunks of material were thrown away from the Earth. Eventually, these chunks came back together under the force of their own gravity to form the Moon. When a comet approaches the Sun, the icy nucleus begins to vaporize. This causes a huge cloud of dust and gas, called a coma, to form around the nucleus. Dust and gas exit from jets in the nucleus and stream away from it, sometimes in two separate tails. The gas tail, shown in blue, is pushed in a straight line directly away from the Sun by the pressure of photons in sunlight. The dust tail, shown in yellow, is also pushed away by photons. The Sun's gravity has more effect on the dust grains than on the gas particles, and so the dust tail curves slightly. When the nucleus begins to move away from the Sun, the tails are actually in front of it as they're pushed away by sunlight. The tails gradually fade and the comet is once more only an icy nucleus. New tails will appear when the comet's orbit brings it back to the Sun. When the Sun begins to swell in about 5 billion years' time, it will heat up the planets until some eventually reach temperatures of millions of degrees. Mercury and then Venus will be melted and engulfed by the expanding Sun. Although the Earth may not be engulfed, the Sun's heat will render the planet lifeless. The Sun will spend around 100 million years as a red giant. Then its loose outer layers will slowly drift off, leaving behind a tiny white dwarf star that will gradually fade away. The gravitational field at the surface of a supernova's core is so strong that light leaving it is, to some degree, pulled back, depending on the angle at which the light rays leave the surface. Inside the contracting core is an imaginary surface called the event horizon. The closer the core gets to the event horizon, the stronger its surface gravity is, and the more the light rays are bent. Eventually, only vertical rays can escape. Once the core contracts beyond the event horizon, no light can escape at all. To an observer, the core would seem simply to vanish. The region inside the event horizon is called a black hole, because nothing inside it can be seen from outside. Inside the hole, the core continues contracting until it becomes a singularity, a point of zero volume but very high mass. The gravitational field of the singularity may attract gas from a nearby star. The gas forms a swirling disk around the hole before disappearing into it. A beam of light traveling across a stationary lift will do so in a straight line. If a force is applied to the lift so that it accelerates upwards, the path of the light beam relative to the person in the lift will be affected. There is no noticeable effect at low accelerations, but in a lift subjected to an enormous acceleration, the beam will appear to curve downwards. According to Einstein, the effects of gravity and acceleration are indistinguishable. An enormous gravitational force will have the same effect on a light beam as an enormous acceleration force. This orbit shows two identical stars following the same orbital path around a common center of mass, which is marked with a cross. Here, two identical stars travel in separate but similar orbits around a common center of mass. This orbit shows what happens when an object of comparatively low mass, such as a planet, orbits an object of much higher mass, such as a star. The Mercury craft had a bell-shaped capsule designed to carry one astronaut. Most of the Mercury capsules were launched by an Atlas rocket. Mercury was also equipped with an escape rocket situated on top of the capsule. If the Atlas rocket malfunctioned during a mission launch, the escape tower's rockets fired, pulling free the Mercury capsule, which was propelled upwards and safely away from the main rocket. The escape rocket was then jettisoned and the capsule splashed down into the sea. If the thrust of the launch rocket does not provide the spacecraft with enough speed to escape into orbit, it will fall back to Earth. With the right amount of thrust, a spacecraft will attain sufficient speed to reach space and enter Earth orbit, held there by the pull of the Earth's gravity. The higher the thrust of the launch rocket, the greater the speed that the spacecraft will attain and the longer the ellipse of the orbit will be. Eventually, with enough thrust and sufficient speed in the right direction, a spacecraft is able to escape the pull of the Earth's gravity and travel to other planets. The Big Bang occurred around 15 billion years ago. The first hydrogen and helium atoms formed within minutes of the explosion. These eventually turned into clouds of gas, which around 14 billion years ago began to condense due to the effects of their own gravity. Over the next 2 billion years, the first galaxies began to form from these clouds of gas. Our galaxy, the Milky Way galaxy, began to come together around 10 billion years ago. Within this galaxy, our own sun was born around 5 billion years ago, with the planets, including Earth, forming from the surrounding disk of spinning gas and dust. At the heart of an active galaxy lies a spinning black hole that attracts gas, dust and stars towards it. Nearby stars are torn apart as they join a disk of material spiraling around the hole. As the material spirals into the hole, it emits intense radiation, causing the disk to shine brightly. In certain active galaxies, radio galaxies, two jets of gas particles shoot from the inner edge of the disk through the galaxy into space. There they form two huge clouds that can be detected only by a radio telescope. The Galileo probe was launched in October 1989 against the direction of the Earth's motion around the Sun. As it fell towards the Sun, Galileo's speed was increased by means of a gravity assist or slingshot from its flyby of Venus. Heading back in December 1990 for a flyby of the Earth, it used a gravity boost to project it into an elliptical path through the asteroid belt, passing by the asteroid Gaspra in October 1991. Galileo then made a second Earth flyby in December 1992, before heading again through the asteroid belt, passing by the asteroid Ida in August 1993, and reaching Jupiter on the 7th of December 1995. For this spacecraft to move forwards, it must fire the rockets to its rear. If the spacecraft needs to slow down, it fires its forward engines against the direction of its movement. In order to turn around, the spacecraft fires its diagonally opposite thrusters, and then fires the thrusters adjacent to these in order to slow down and maintain its new position. Launched from the Space Shuttle Atlantis in May 1989, the Magellan probe fired its motors to send it towards the orbit of Venus. After flying close to the orbit of Venus, Magellan continued its journey by returning towards the orbit of the Earth. After making 1.6 orbits of the Sun, Magellan reached Venus in August 1990, firing its rocket motors to slow it down. Magellan went into an elliptical near-polar orbit around Venus, taking it between 249 and 8,543 kilometers from the surface. Each set of measurements took 243 days, the time it takes Venus to turn once on its axis. During a meteor shower, the individual meteors or shooting stars look, from our viewpoint on the Earth, as though they are shooting across the sky in different directions. The meteors in fact travel along parallel paths, and we see them as if they were traveling towards us along the sides of a long tunnel. If lines are drawn to trace back the paths traveled by the meteors, the lines all meet at a single point. This point is called the radiant. The name of the constellation in which the radiant lies provides the name of the meteor shower. The radiant of the Leonid meteor shower, for example, lies in the constellation of Leo. Pluto and its moon Charon take exactly the same time, 6.4 Earth days, to orbit once around their common center of mass. During each orbit around the common center of mass, Charon also rotates exactly once about its own axis. This situation is called synchronous rotation. Like Charon, Pluto also rotates once on its axis during each orbit of the center of mass, and so it also has synchronous rotation. This means that the motions of the planet and moon are locked together. An observer on the side of Pluto that faces Charon would see the same side of the moon fixed in the same position in the sky at all times. An observer on the other side of Pluto would never see Charon. Stars that appear to be of equal brightness when viewed from the Earth, such as the two stars represented here, are said to have the same apparent magnitude. When lines of distance are drawn in, we can see that the stars lie at different distances from the Earth, and that their apparent magnitude is not a true measurement of their brightness. Imagine that both stars are moved to an equal distance from the Earth. The distant star appears brighter as it gets closer, while the nearest star appears dimmer the further away it gets. When the two stars are side by side, the difference in their true brightness or absolute magnitude, becomes obvious. Return them to their original positions and the stars again appear to be of equal brightness. The third stage of the Saturn V rocket took the Apollo craft into a low Earth orbit, where the craft's systems and equipment were checked by ground control. Once this was done, Saturn V's third stage was fired again, putting Apollo on its trajectory for the Moon. Next, the command and service module separated from the third stage of Saturn V, which opened to reveal the lunar module. The command and service module turned around to dock with the lunar module. The whole spacecraft then separated from the third stage, which was jettisoned, and the journey to the Moon continued. As it drew close to the Moon, Apollo slowed down and entered lunar orbit. With 2 astronauts on board, the lunar module separated from the command and service module and landed on the lunar surface, using its retro rockets to slow it down for a safe landing. The command and service module remained in lunar orbit with 1 astronaut on board. The lunar module took off from the surface of the Moon to redock with the command and service module in lunar orbit. After the crew had transferred, the lunar module was jettisoned, crashing back onto the Moon's surface. The command and service module engines fired, and the journey back to Earth began. As the craft approached Earth's atmosphere, the command module separated from the service module. The service module burned up, but the command module, containing the astronauts, was protected by its heat shield from the heat of re-entry and went on to splash down in the Pacific Ocean. Just before it re-entered the Earth's atmosphere, the Vostok craft turned round and its retro rocket fired to slow it down so that it would fall back towards the Earth. The equipment module separated from the capsule and both components re-entered the atmosphere. The equipment module burned up, but the capsule containing the cosmonaut was protected from the intense heat by its heat shield. At a height of approximately 7 kilometers above the Earth's surface, the cosmonaut ejected from the capsule and both cosmonaut and capsule parachuted to the ground. Time may be thought of as a line running vertically up a page. Space can be measured in a line running out from the timeline at 90 degrees. Your lifeline, or world line as it is also called, moves somewhere in between the two. If you were to stand perfectly still, your lifeline would travel straight up. Time would pass, but your position in space would not change. If instead of standing still you were to move at a constant speed in a particular direction, your lifeline would be straight but inclined from the vertical. The faster you travel, the more your lifeline inclines. In reality, most people travel at various speeds through life, and so their lifelines tend to be irregular. According to the steady-state theory, the universe looks the same from any viewpoint and at any moment in time. This theory also states that the density of the universe remains constant despite its continuous expansion. This is said to be achieved by the creation of new matter in the form of hydrogen gas, the raw material for new stars. The Sun is at the center of the solar system, holding the planets in stable orbits around it. The planets travel fast enough to avoid being pulled in by the Sun's gravity, but not so fast that they escape its pull and leave the solar system altogether. The 5 outer planets, which we see here, move more slowly than the inner planets because the Sun's gravitational pull is weaker at such great distances. The 4 inner planets experience a greater gravitational pull from the Sun, and so they must travel faster than the outer planets in order to maintain their orbits. The nearer they are to the Sun, the faster they must travel. Mercury, the closest planet to the Sun, travels at approximately 172,000 kilometers per hour, more than 10 times faster than the furthest planet, Pluto. The young, rapidly spinning Earth was initially fluid because it was very hot. The separation theory, no longer accepted as possible by astronomers, says that as the Earth spun, rotational forces caused a bulge to develop that eventually separated from the Earth to form the Moon. According to the sibling theory, the Earth and Moon formed at the same time from the cloud of gas and dust that was spinning around the young Sun. They formed so close to one another that gravity has kept them together ever since. The captive theory says that because the moon's rocks are different from rocks on Earth, the two objects must have formed in different areas of the solar system. Later, the moon passed so close to the Earth that it was captured by the Earth's gravitational field. As this rocket is slowly passing by a planet, an identical rocket approaches at very nearly the speed of light. As the second rocket passes the first, it appears to us to be shorter in length because objects contract in the direction of their motion. Contraction in the direction of motion is not visible at everyday speeds, but at speeds approaching the speed of light, it becomes much more apparent. All the planets orbit the Sun in the same direction, anti-clockwise when viewed from above the North Pole looking south. Here we see the Earth and Mars moving around the Sun. Also shown is the path of Mars through the sky as seen from Earth, known as its apparent orbit. The Earth is closer to the Sun and moves faster than Mars, which seems to move from west to east in the night sky during the course of a year. Here, the Earth is catching up with Mars. If you looked at the sky on successive nights, Mars would be moving from west to east. As we get nearer to Mars and overtake it, the planet appears to change direction because it starts to move from east to west in the sky as seen from Earth. Then, as the Earth speeds away from Mars, Mars resumes its usual path from west to east. The small backward loops in the apparent orbit of Mars that occur about every 25 months are simply a trick of perspective, caused by the fact that the planets move at different speeds in their orbits around the Sun. The orbital path of the Earth around the Sun lies in a plane, an imaginary flat surface, called the ecliptic. The orbital path of the Moon around the Earth is tilted away from the ecliptic by about 5 degrees. The angle is exaggerated in this view. During each lunar orbit, the Moon passes through the ecliptic twice at points called nodes. A full eclipse can occur only when the Moon is at one of its nodes, and only when the Sun, Moon and Earth are aligned along the imaginary line that joins the nodes. This line can be clearly seen when viewed from above the North Pole. Under these conditions, the Moon casts its shadow on the Earth when the Moon is at the node between the Sun and the Earth. An observer inside the shadow then sees a solar eclipse. And when the Moon is at the other node, the Earth is between the Sun and the Moon. The Earth's shadow then falls on the Moon and causes a lunar eclipse. If the Earth moves a short distance further along its orbit, the Sun, Earth and Moon are no longer aligned when the Moon is at one of its nodes. In this situation, no eclipses occur because the Earth and the Moon can no longer cast their shadows on one another. A star is a spherical mass of gases held together by gravity. The gases are pulled towards the star's center, where they become densely packed, which causes them to heat up. In the core, hydrogen gas is hot enough to undergo nuclear reactions. These reactions release energy in the form of tiny particles called photons that radiate outwards. These photons exert an outward pressure on the star's material, balancing the inward force of gravity and keeping the star in a stable state for millions or even billions of years. Most of the energy radiated from the star's surface is in the form of heat and light. The shuttle takes off vertically using the 2 rocket boosters and its own 3 rocket engines, which burn fuel from the external tank. About 2 minutes after liftoff, the rocket boosters burn out. They fall away from the rest of the shuttle and parachute back to Earth, where they are recovered from the sea by retrieval crews. Just before reaching orbital altitude, the external tank separates and tumbles back into the atmosphere where it disintegrates. The Orbital Maneuvering System engines place the plane in orbit. To re-enter the Earth's atmosphere, the orbiter is rotated so that the rockets can be fired against the direction of flight, slowing the plane down. As it descends, the orbiter is turned again. It re-enters the Earth's atmosphere nose up with the heat-resistant tiles on the underside of the plane bearing the brunt of the friction. The orbiter glides down to the airstrip without using its engines and lands at about 345 kilometers per hour. Mercury's year, the time the planet takes to orbit the Sun, lasts for about 88 Earth days. While it orbits, Mercury spins on its axis. It takes 2/3 of a Mercurian year, or about 59 Earth days, to spin once, as is made clear by the marker shown on the planet's surface. This length of time is Mercury's sidereal day, and is measured according to the positions of the stars. Now, imagine you are standing on Mercury, and the Sun is about to rise. You remain in sunlight all the time during one orbit of 88 Earth days, while Mercury spins 1.5 times. During the next orbit, you're in darkness all the time. At the end of this orbit, the Sun is about to rise once more. Inside the spinning disk of gas and dust that surrounded the young Sun, tiny dust grains were colliding and sticking together to form larger and larger objects. In this way, the 4 rocky inner planets were formed. The asteroid belt consists of small rocky objects that failed to stay together to form a planet. Further out in the disk, where it was cooler, the rocky cores of the large outer planets formed in the same way as the inner planets. Here, however, the gravity of the cores attracted the gases that swirled around the Sun, so forming the large gas planets. In the outer region of the disk, tiny lumps of ice and dust were flung into the outer reaches of the solar system by the gravity of the gas giants, where they formed a huge cloud of comets. The exact origins of rocky Pluto, the 9th planet, are at present unclear. Stars are born inside huge spinning clouds of gas and dust. When a region in the center of a cloud gradually becomes denser than the surrounding material because of the effects of gravity, the temperature of this dense region increases and the heated cloud starts to glow. The dense matter slowly breaks up into hundreds of clumps of gas and dust called protostars. Each protostar spins and continues to contract and heat up. Eventually, the core of each protostar is dense enough and hot enough, about 10 million degrees centigrade, for nuclear reactions to begin, and the protostar becomes a fully fledged star. When a Cepheid variable star is at its largest, gravity forces the outer layers to contract. Its gases become compressed and trap some of the energy radiated inside the star. The star then dims. The radiation pressure increases, eventually overcoming the inward force of gravity and pushing the gases outwards. As the star expands, it suddenly brightens as the trapped radiation escapes. Once the pressure has lowered sufficiently, the star contracts, continuing a regular cycle. Almost all satellites receiving and sending television signals are in geostationary orbit, always situated over a fixed point on the equator. Yet, by a careful arrangement of beams, signals can be sent to a particular area at any latitude on the Earth's surface that is within sight of the satellite and not too near the Earth's poles. The satellite antennae are designed to give the beam the correct shape to cover just the target area, such as Australia. This shape is called the satellite footprint, and individual dishes within the footprint receive a strong signal from the satellite. The number of spots on the Sun follows a cycle lasting around 11 years. At the beginning of the cycle, there are few, if any, sunspots. The first spots appear about 1/3 of the way between the Sun's equator and its north and south poles. Over the next few years, as old spots fade away, new spots appear in increasing numbers closer and closer to the equator. The final stage of the cycle is known as the solar maximum, during which there may be 100 or more spots visible at any one time. Light enters the telescope, hits the main mirror and is reflected to a second mirror. It then travels back towards the primary mirror and through a hole in its centre. The image forms behind the mirror, where it can be viewed through an eyepiece or recorded by a computer. Light enters the telescope and is reflected by the main mirror, which focuses the light above it. A smaller mirror, aligned at an angle to the axis of the telescope, intercepts the beam, directing it to an eyepiece on the side of the telescope. Light enters the telescope, hits the main mirror, and is reflected back to the second, smaller mirror. This diverts the light to a third mirror, which directs the light to the side of the telescope. The focus remains fixed as the telescope pivots on its mount. At the focus, heavy or delicate instruments can be used to study the image. The moon spins exactly once on its rotational axis during the time it takes to complete one orbit around the Earth, which is 27.3 days. This results in the same side of the moon, the near side, always facing the Earth. As the moon rotates, different areas of the lunar surface become sunlit while the moon orbits the Earth. From Earth, we cannot see the new moon because the near side is in darkness. The near side then gradually becomes fully sunlit before falling back into darkness when one orbit is completed. The boundary between light and dark areas of the moon is called the terminator. 250 million years ago, three huge landmasses drifted together to form one giant landmass called Pangaea. This was then split by the Tethys Sea into Laurasia and Gondwanaland. 120 million years ago, Laurasia began splitting, with North America moving away from Europe. Gondwanaland also split, and India began drifting towards southern Asia. The land masses continued to shift until they reached the positions we recognize today. Millions of years from now, the Americas will be further west and Africa will have joined Eurasia. What happened in the initial moment of the Big Bang remains a mystery, but it's likely that after only the tiniest interval, the universe was still smaller than the nucleus of an atom. Almost immediately, the strong nuclear force and the electromagnetic force separated, providing the energy needed for the universe to start inflating. Before even a millisecond had passed, the universe had grown to about 3 times the size of the Sun. Continued inflation caused the universe to double in size every fraction of a second. As Luna 9 descended towards the surface of the Moon, a hinged arm extended from the craft. When the arm made contact with the surface, the capsule containing transmission equipment separated from the main body of the craft. The capsule dropped onto the Moon's surface. Because its base was weighted, it came to rest the right way up. The main craft crashed onto the surface. Next, the outer sections of the probe began to unfold. With the panels open to stabilize the capsule, the antennae were extended and a television camera was revealed. The lander then transmitted the first television images of the Moon back to Earth. 4.5 billion years ago, the Earth had a surface of red-hot, semi-molten rock. Over millions of years, the surface began to cool and form a solid crust. Hot gases and lava bubbled up from below the surface, erupting from volcanoes to form a thick atmosphere. At the same time, meteoroids were smashing into the surface, forming thousands of craters and sending dust into the atmosphere. Before the Earth was 1 billion years old, it had cooled enough for water vapor in the atmosphere to condense into drops. These drops fell in rainstorms for millions of years, clearing the atmosphere and creating the oceans. The Earth was beginning to resemble the world we know today. The shapes of the various orbits can be reproduced by cutting slices through a cone. The first slice, made parallel to the base of the cone, reveals a circle. Of the objects in the solar system, Venus comes closest to following a circular orbit, although no object orbits in a perfect circle. The next slice, made at a slight angle to the base of the cone, reveals an ellipse. Many celestial objects follow this orbit. Of the planets in the solar system, Pluto has the most elongated orbit. The third slice, made parallel to the opposite side of the cone, reveals a parabola. Unlike the previous orbits, the parabolic orbit is an open-ended curve, so an object following such a path would never return to its starting point. The fourth slice, made at an even more upright angle, produces another type of open-ended curve called a hyperbola. Many comets follow near parabolic or hyperbolic orbits, passing once around the Sun, never to return. In October 1990, while in orbit around the Earth, the space shuttle Discovery released the Ulysses probe into space. Ulysses used its 2 rockets to propel it 920 million kilometers towards Jupiter, where it arrived 16 months later, making its closest approach on the 8th of February 1992. Assisted by Jupiter's gravity, Ulysses changed trajectory and veered south of the Sun's ecliptic plane, heading towards a region in space from which it could observe the Sun's southern pole. In late June 1994, Ulysses started observing the Sun's southern polar region. For 4 months, it flew between 420 and 285 million kilometers above the area to take measurements. Ulysses' orbit around the Sun then took it northwards, and it crossed the Sun's ecliptic plane in February 1995. Ulysses began to observe the Sun's northern polar region in June 1995 and had completed its study of the area by October 1995.